Okay, so good morning, everyone. So welcome to this third day of the VPHi Summer School. So first day, so we had clinical, biological insights, so that show basically the complexity of the problems we have to face. So either in biology, pathophysiological processes, medical image analysis. Yesterday, so we've seen different examples on how data are integrated into models, so machine learning models, and also mechanical models, so for the exploitation of medical images and patient data. And then, so today is the first day where we dive a little bit more, and modeling technologies. So we'll have then the approaches of modeling at different scales, so still with the incorporation of data. And then it's my pleasure to welcome Sandra Loerakker, who is kicking off then this third day. So Sandra is Associate Professor at the Eindhoven University of Technology in the Netherlands. So she obtained her PhD in the same university in 2011, and for which she was awarded the ESB Best Doctoral Thesis Award in Biomechanics. Wow, so the award is running since a long time now, I'm seeing.
I was the first, I think.
Yeah, wow, that's good. And then, so she also won the EPUAP Novice Investigator Award in the same year, so 2012. She formed part of this the Northwestern University in the USA, and she also collaborated with the University of Alberta in Canada. And in 2015, then after this international collaboration, so she was appointed as assistant professor at TUI, and in 2019 she was promoted as associate professor. And she got a Marie Curie individual fellowship by the European Commission, so starting 2016. And then she decides the university to be a visiting professor at Stanford University in the USA. And the research of Sandra focuses on developing experimentally informed computational models to understand and predict how mechanical factors regulate soft tissue regeneration and adaptation, with focus on cardiovascular regenerative medicine. So she has been then the recipient of an ERC starting grant, so in 2018, and then she got also a major grant by the Dutch Science Foundation, which is the VD grant, in 2022. And so she's also teaching, and we all have different hats at the university. And then she was elected as the best master teacher of TUI's biomedical engineering department. So guys, students, size the opportunity. You also have a great professor on top of great researcher. And in 2024, so she became elected member of the Council of the European Society of Biomechanics. So Sandra, that's a pleasure, and then the floor is yours.
Thank you very much, Jerome, for the kind introduction and for not putting any pressure on me. So, I'd like to really welcome everyone. If you have a question or a remark, just feel free to interrupt me, right? So this is a long talk, so I don't mind getting questions in between. It's fine? Okay, thanks. No problem. All right, so my talk will be about computational mechanobiology models that we apply to advance cardiovascular regenerative medicine. That's basically the main thread in my whole presentation. So why regenerative medicine for cardiovascular tissues? Just pressing this button, right, or not? Doing I something wrong?
No, it should work.
Otherwise, I would just use it there.
Use the button now?
Yeah, now it works. Thanks. All right, so yeah, why cardiovascular tissue? So we learned already in quite of the talks yesterday that I attended that our cardiovascular tissues age quite substantially, maybe more than other tissues, right? And the tissues that we mainly look at are heart valves and blood vessels. And I think you all know that these tissues deteriorate over time with aging. So if you look at heart valves, they typically calcify, and the calcification increases the resistance of these valves, which means that the heart is overloaded, which can lead to heart failure. So this is a serious problem that needs to be solved. Also arteries, you know, they can get blocked via plaque formation or other reasons, or they can dilate, that's another problem. And the main thing is that many of these tissues, when they get diseased, then there are only limited repair strategies, and they often need to be replaced by artificial materials. And there's different options for that. So here on the left side, I have 2 examples for heart valves. On the right side, I have 2 examples for blood vessels. So you have synthetic materials. So you have these, this is the pointer. Yeah. So you have these synthetic materials from mechanical heart valves, synthetic vascular grafts. So the main advantage of these types of grafts is they're readily available, right? You can just make them in large numbers. They're also very durable, at least in case of heart valves. But there's also quite some limitations. So these mechanical heart valves, they tend to lead to thrombosis problems because they're just not like native heart valves, right? They lead to different flow dynamics, which can lead to a lot of problems, and people need to take anticoagulation therapy for as long as they have these valves. Synthetic grafts also lead to many problems, particularly when you implant them as small diameter vascular replacements. So you can also replace these tissues with biological materials. So these are dead materials. I want to emphasize that. So they're not living. So you have bioprosthetic heart valves. They look a lot more like native heart valves, so the functionality is a lot better. But the functionality also deteriorates over time because these tissue materials just degrade and calcify. There's similar problems with autologous blood vessels. So the availability is limited because you just don't have an unlimited supply of these blood vessels. But if you have them, then this typically works well. So long story short, there are some replacement options, but they also have serious limitations. And the main limitation is that all of these materials are not living. And living materials, they can grow, they can adapt to changing circumstances, they can repair, and that doesn't apply to these kind of materials. And this particularly forms a limitation for pediatric patients. So if you have a congenital malformation of your heart valve or a blood vessel, and you need one of these materials, then that means that you need several replacements throughout your life because you outgrow your valve or vascular replacement. So what if we could build actually living tissue replacements? So that's what we are looking at. So can we rebuild healthy living heart valves and blood vessels? And our main focus is on heart valves. So one way to do that is via tissue engineering. And the aim of tissue engineering is to really cure diseased tissues by rebuilding living tissues inside the body. So here's an animation of how that works for a heart valve. So this is the heart. And then if you have a diseased heart valve, then you can replace that diseased heart valve with a synthetic material, which is the function of a heart valve. It's a porous synthetic material which immediately takes over the function of the diseased heart valve. And then over time, it regenerates in the body, inside the body. So you basically regrow your own living heart valve. That is the principle. So as you can imagine, this is quite a complex process. It involves a lot of biological processes, and many of these biological processes are also depending on the mechanical environment that these tissues are subjected to. So to zoom a little bit into that, so here we start off with this biodegradable scaffold material, which can either be in the form of a blood vessel or a heart valve. So this is made of polymeric material. It's biodegradable. It's being degraded via oxidation or by the cells, via enzymatic degradation. But it is a foreign material. So a foreign material triggers an inflammatory response. So your own immune cells invade these foreign materials. At the same time, or afterwards, it goes a bit hand in hand, these inflammatory cells attract other cell types. And these different cells, they can produce new extracellular matrix. So while these cells produce new extracellular matrix and basically rebuild your new tissue, the inflammatory cells make sure that the polymer material is degraded to ultimately end up with a living tissue without any polymer remnants. That's the concept of tissue engineering. So biologically, this is quite complex because you have multiple cell types involved. We also know that all these different cell types, their behavior is dependent on the mechanical environment that they are subjected to, so that further complicates things, because whenever you have a change in your material composition, that also changes the mechanical environment. So it's a really complex feedback loop. And the main challenge is that these constructs need to remain functional throughout the entire procedure. So, because you cannot just live with a non-functioning heart valve. So it really needs to stay functional all the time. And this is not so easy. So there have been quite some preclinical studies that have been done. And there have been quite some promising examples where they saw nice tissue outcomes, nice functionality. But we also had a lot of failures. And the main problem is that we don't really know when something is going to work and when something is going to fail. So it's basically a lot of trial and error research. It's very ineffective. And you can imagine this, you cannot bring something like this to the clinic if you have no idea if it's going to work and when it's going to fail. So what complicates this is that we have only a limited understanding of the underlying regenerative processes, so the influence of the different cell types and how that influences the transformation of a synthetic scaffold material into a living tissue. It's also complex because the design space for these scaffold materials is huge. The chemists can make a lot of different materials. They can organize them in different ways, which is very nice because you can really tailor the design. But we don't know what the design criteria are. What should we do here to make sure that the end outcome is good? We don't know that. So what we try to do in our group is to develop computational models to get more understanding of this black box of regenerative processes, particularly looking at the effects of mechanical factors on regeneration, in order to predict what happens to a scaffold if you implant that into the body, and then identify what you should do, maybe differently or a completely different approach, to get better outcomes. And in the end, we hope that this is a more effective, more efficient approach to design next experiments. So going away from trial and error to more informed experiments. So basically to sketch what we're doing, so we're looking at, and we're developing growth and remodeling algorithms. With growth, I mean that we model the increase in mass or volume of a tissue. And remodeling, I mean with that the organization of the tissue changes. So you don't get more tissue, but the organization can change. And all of these things, they have an influence on the mechanical properties and thus the functionality of the tissue. So we do that by integrating experimental work with computational modeling. So the experimental work I always do in collaboration with my colleagues or other people, because that's not my expertise. But these experiments are really important to inform our computational models and also to validate them. Then in terms of applications, we don't only look at these tissue engineering examples, first of all because there's limited data, but I think we can also learn a lot from how native tissues develop. So how do they develop in a healthy way? What happens if they get diseased? And how can we leverage that knowledge to improve regenerative medicine? So we really try to integrate all of that. So in this presentation, I would like to show you some examples of our research in 3 different areas. So the first one is about remodeling, and particularly the influence that cells have on the change in tissue organization. It's a bit older work, but it shows you kind of the concept of how computational models can make a difference in regenerative medicine. The second part is actually focusing more on the biological mechanisms of growth and remodeling. So we don't only try to know what happens, but also why that happens, because sometimes you can also interfere in one of these processes to also have an impact on regeneration. And lastly, this is the most recent work. We have been developing models where you really integrate growth and remodeling simultaneously. And this is really necessary to model the transformation of a synthetic material that should degrade over time, so you have negative growth, and the buildup of a new tissue, so that's positive growth. So let's start with the first part about the cell-mediated remodeling processes. Our motivation for looking at that was a failure mode of tissue-engineered heart valves, which was seen in basically all the groups in the world that worked on heart valve tissue engineering. So this is an example from our own group more than 10 years ago. So this is these are the results of a preclinical study of a heart valve that was implanted in a sheep. So this is the implant. And then, let's say after 2 months, when it is explanted, it still looks pretty nice. So you see new tissue formation, the valve looks functional, so it's all good. But then the more long-term explants, up to about half a year, they show that these leaflets really get shorter over time. And you can imagine if the leaflets get shorter and the valve is supposed to prevent backflow towards the heart, then these valves are no longer functional. So we have replaced a non-functional valve with another non-functional valve in the end. So this was really a serious problem. The root cause of the problem was known. It's the fibroblasts that typically invade these valves after implantation. They're known to exert a lot of contractile forces on the extracellular matrix, so particularly collagen fibers. So you can imagine that if you look at this movie of this fibroblast pulling on a collagen fiber, that that they are responsible for this retraction of these leaflets. But the question then is, what can you do to change the outcome, to minimize this retraction of the leaflets? Because we cannot influence the cells that are invading the tissues, but maybe we can influence their behavior or the results of their behavior. But for that, we need to understand how it works. So we developed a computational framework in our group. So I worked on this myself as a postdoc, but also a colleague of mine, Tommaso Ristori, who is now an assistant professor in the group. He also contributed to this development. I'll only show you the concept of these models. So we look at fibroblasts like cells inside a collagen matrix. And what we do, we have algorithms for how these cells change their organization and contractile forces in response to both mechanical stimuli, but also structural stimuli. So, for example, the organization of the collagen network in the tissues. So here you see a movie of the actin cytoskeleton of a fibroblast, and is known to reorient in response to mechanical cues. And we have algorithms to capture that behavior based on experimental inputs. And we also included a mechanism for how these contractile forces of these fibroblasts are then transferred to the collagen fibers, which can then lead to retraction. And finally, we included a mechanism which is, I think, well known in the biomechanics field, that the degradation of collagen fibers is strain dependent. And typically, strain protects collagen fibers from degradation. So this is incorporated in many remodeling models in the field, but the influence of the cells was less included. And we use this framework to analyze both native heart valve development, but also tissue-engineered heart valve remodeling. So I will give you an example of these two applications in a minute, but first I'll show you how we built that model. So we implemented these mechanisms based on known in vitro experiments, so the behavior that was seen in those experiments, and then we put everything together to see, okay, can we then capture the overall remodeling of engineered tissues? So we always try to start as simple as possible. So we started with just modeling static tissue, so just constrained in the lab. So this is a uniaxially constrained engineered tissue strip. And if we just model a quarter of this tissue, so this top right quarter, then we saw that we could indeed model this compaction of this tissue, so it decreases in width in the center, and also the alignment of the collagen fibers, which are the spider plots over here. So we could actually capture what was seen in the experiments. A more complex case was the remodeling of a statically loaded vascular graft in the lab. So we knew from experiments that the organization changes from the inner side, where the collagen fibers are circumferential, towards the outer side, where the collagen fibers are oriented more in the axial direction. And this was also captured with our computational framework, this change in organization from inside to the outside. And then finally, when we tried to model the remodeling of non-loaded tissue-engineered heart valves, our model predicted that these valves would really retract substantially, so really leading to an almost triangular opening of the valve. And this was also very much in line with what we saw in the lab. So yeah, given these comparisons, we thought, okay, now it's we can take a next step. So, and one of the things that we looked at was the development of the collagen architecture in native heart valves. So we analyzed human samples of heart valves. These were valves from donors, and these valves could not be used for transplantation, so then they could be used for research. Here you see an overview of the collagen architecture in these different valves. Here are some aortic valves of different ages, and here are some pulmonary valves of different ages. And this is a fetal heart valve. It doesn't have the same scale as the other valves, obviously, it's much smaller. But we really wanted to understand, okay, well, if you look at this fetal heart valve, which has a very limited organization of the collagen network, can we then understand how this collagen network evolves into a much more aligned collagen structure, which is really critical for the valve's mechanical function. So to just zoom into that, so this is the fetal heart valve. I hope you can appreciate that all the green is the collagen fibers, that we do have a little bit of alignment, but it's not very strongly aligned. This is an image of a pulmonary heart valve of an adult, and there you really see the strong bundles of collagen fibers that are aligned in this circumferential direction of the leaflets. So we wanted to understand what are the mechanisms that actually enable this organization to emerge. So we started from our fetal heart valve. These are the experimental data in red here, so showing a small peak and in the zero angle direction, which is the circumferential direction. And we first thought, okay, most remodeling models just look at the strain-mediated remodeling of collagen fibers without the influence of cells. Can we then actually understand why we have this alignment in the fetal stage? And well, the result was no, we cannot. You just don't get any alignment. If you just don't include the influence of cells, so you don't include the influence of the contractility, which is really high before birth, and contact guidance means that the cells tend to orient along the direction of the collagen fibers that they are connected to. If you don't include any of these processes, you just don't get any alignment in these heart valves. So it's not only the strain-mediated collagen degradation that can lead to this. Then we turned on the contractility of our fibroblasts in the valves, and we actually could get a very nice match with the experimentally observed collagen alignment. So we were very happy with this, and we actually thought, oh yay, we have found the main mechanism. But when we let the model run for another 5 years, it actually showed that we were not capturing everything. So because the actual collagen organization in native heart valves is increasing with age, and our model actually predicted the opposite. So yeah, this definitely showed we were missing something. So then we turned on this contact guidance mechanism, which leads to the cells also reorienting not only in response to their mechanical environment, but also in response to the structural environment. And then we could at least qualitatively capture this increase in collagen alignment. So what it shows is that you need this initial contractility, which is really maximal before birth, to get the initial emergence of the anisotropy of the collagen architecture, but you need the alignment to structural cues to actually get a reinforcement of this collagen organization over time. So in this way, we could understand more about what are the key players leading to this organization. Then for the tissue-engineered heart valve, so here we were really focused on understanding what are the root causes of this retraction problem. So we modeled the remodeling of our engineered heart valves with the same properties of our valves in pulmonary loading conditions, because most of the animal experiments are done by implanting valves in a pulmonary position, so with low hemodynamic loading. And then if we assumed kind of a basic fibroblast contractility level, which was mostly resembling with the in vitro data that we had, then our model predicted that these valves were indeed retracting. So this image here shows the valve in its diastolic configuration. So in diastole, the valve should close to prevent backflow, and our model showed that it cannot close enough in diastole to prevent backflow. So indeed, this could explain why we were seeing these failures in the experiments. The collagen architecture, which was also predicted here with the spider plot, showed that we could still get a slightly circumferential organization, which also matched qualitatively with the experimental outcomes. So then the question that we asked was, okay, so now our model indeed predicts that this is indeed something that happens in these in vivo experiments, but what can we do to prevent this problem from happening? Can we just, if cell contractility would be reduced, could that then solve the issue? So in the model, you can easily change parameters. So we reduce cell contractility, and this showed that we really need to increase cell contractility substantially in order to get a valve that remains functional. And then the other thing that the model predicted then, that if you're able to do that, then the collagen orients in the wrong direction, basically. So it's, yeah, you switch one problem for the other problem. So main conclusion, remodeling in the pulmonary configuration of these heart valves is probably not easy to get it right. We also did simulations, or actually predictions, for remodeling in the aortic position, and actually there the results were a lot better, because apparently the hemodynamic loading, which is higher in the aortic position, can compensate a lot more for these contractile forces of the fibroblasts. So you get a different equilibrium, and in all of the cases that we simulated, our valves were able to close in diastole, and they also all obtained a circumferentially oriented collagen organization. So this shows that, I mean, the main problem with aortic valves is that you need a much stronger materials to withstand these pressures. But if that works, then probably the remodeling is much more favorable than in the pulmonary position. But then still, we also want to make a valve for the pulmonary position. So can we do something else? Maybe can we change the valve design to improve outcomes there? And there we were inspired by native valve mechanics. So this is an image of a native aortic valve, which has this strongly aligned collagen fibers. And they have really a mechanical function because the material is very anisotropic. So if you load this material in diastole with a pressure load, then it extends mainly in the direction perpendicular to the fibers, which you can also see here in this illustration. So you get much larger strains in the radial direction, so towards the center of the valve, than in the circumferential direction. And this is really beneficial for valve closure because you're basically pushing the leaflets towards each other. So it has a reason why that actually works well. And of course, we knew that our engineered valves were not the same as the native valves, but the question was, how far are we off from this preferred mechanical function? So then, we did some simulations. So we tried to replicate the mechanical state of our tissue-engineered heart valves, and this is what we saw for the radial strains, and we were at first really surprised by that. Does anyone know why, if you look at this image? What is wrong with these strains that we see over here? I first thought that I did something wrong because it's really non-physiological. But after doing some tests, it appeared to be true. What is wrong? Does anyone have any idea? So we're supposed to get really high radial strains, right? Because that was what the native heart valves typically exhibit. Our valves actually showed a lot of radial compression. All this blue here means that we're actually compressing the leaflets in diastole. And why is that a problem if you think about tissue remodeling and the contractile cells being present in these heart valves? This means we're actually helping the cells to retract the leaflets, because the cells are really pulling, and what we did with this design, because in the hemodynamic loading leads to compression of the valves. So we're just making it easy for the cells to retract the leaflets. So in hindsight, this was 10 years after the first experiment, so maybe we should have done that earlier. But this really could explain why we had so many problems with this problem of retraction of the leaflets. So then we used modeling to explore what should we do differently to prevent these negative strains. And what we found out was, because this is a stress strain graph, so we have, instead of having large radial strains and small circumferential strains, we really had the opposite. So we had large circumferential strains and actually compressive radial strains. So we found out that if you change the geometry from a relatively straight design towards this more curved design, then you can already get rid of most of the radial compression, so without changing anything in the tissue itself. And if we are then able to also increase the organization of the tissue towards having a stronger collagen alignment, then that model predicted then that we could actually reverse the strain patterns. So of course, this is just a model. It doesn't prove anything. So we went on to explore this with in vivo studies. So that meant that we had to kind of enforce this geometry that was predicted by the model in our tissue-engineered heart valves that we then created in the lab. So we built geometrical constraints to enforce this new geometry in our valves. And in vitro, so in the lab, they actually functioned pretty well. And then we implanted them in a sheep model for 1 year. And this really was a breakthrough because almost all the valves remained functional for the entire year. So here you see some echocardiography data with the cross-section of the heart valves, just at the beginning and also after 1 year. And you can really appreciate here that the valves can still, the leaflets can still touch each other, so they remain functional. So the valve did shorten a bit if you compare the leaflet lengths over time, but at least it stabilized within the first half of the study, and it was only limited, so it did not lead to a loss of functionality. Also surprisingly, we saw that our valves actually remodeled towards a relatively circumferential organization of the collagen network. So this was before implantation of some control samples, and this was after 1 year implantation. And this is an alpha SMA staining, so it is a measure for the contractility of the cells. And it showed that actually our valves, the cells in our heart valves were actually not very contractile. And we still don't know why, but they were less contractile than we had in the previous studies. And our hypothesis is that maybe because we impose a more physiological mechanical state that influences their contractility and their activation. But we actually still don't know why that happened. And we were actually still lucky that this happened. Because with our model, we also did some analysis of, okay, what are the main drivers of this remodeling response? And we varied the contractility of the cells because we cannot control that. And we also had limited control over the leaflet thickness that we obtained in our in vitro culture. We could control the geometry, but not the thickness itself. So we varied these two parameters, and this showed that we were indeed lucky to have limited cell contractility, because this is a top view of the diastolic configuration of our heart valves after remodeling. And then our model indeed showed that that would not lead to too much retraction because the valves can still close in diastole. If we would have had larger contractility, we would have still ended up with non-functioning valves. So it was a bit of luck, but also, yeah, apparently the change in geometry made a difference there as well. Also, of course, we compared the amount of retraction in our models with our experimental data. So we took off the diastolic pressure to compare them to the explant data, and then that showed that this amount of retraction that was in our model was actually resembling quite well the explants. We also had a little bit of retraction. Yeah. All right, and then in terms of collagen organization, I don't want to spend a lot of time on this, but our model basically showed that we have not so much influence on the collagen architecture. It's slightly anisotropic in most cases. And if you compare these predicted organizations to the explant organizations, then for low contractility levels, our predictions actually matched pretty well with the experimentally observed organizations. More importantly, if we account for differences in material properties or thickness of the valves, then we could also explain why certain valves had a more stronger alignment than other valves, and also why one valve that was positioned in the wrong way was actually still retracting. So our model could also explain why certain valves were remodeling in a functional way and why other things were not working. So long story short, this in the end appeared to be a proof of concept study showing that you can really use computational modeling in regenerative medicine to analyze why you get certain problems. So in this case, our retraction problem. So we used the models to explain why this happened, but also to propose a solution, which was then actually, it proved to be successful. So it shows the value of computational modeling, but also shows the relevance of the mechanical environment, because the only thing that we changed was the geometry. We didn't change anything else in the whole protocol. And with the geometry, you have a huge impact on the mechanical state. Moving to the second topic, more into diving into the biological mechanism. So why do things actually happen? So maybe one thing first, so we mainly look into blood vessels here, not because we don't want to do this for the heart valves, but modeling these biological signaling pathways is quite complex. So we prefer to start simple from the mechanical point of view, and blood vessels are mechanically a lot more simple than heart valves. So that was our motivation to look at blood vessels here. And the main pathway that I'm looking into with my group at the moment is the Notch signaling pathway. So Notch is a juxtacrine signaling pathway, which means that you need direct cell-cell contact to activate signaling. So it's known to have a very important role in the vascular wall. So here you see a schematic of the hypothesis of how it works. So you have endothelial cells that express certain ligands, jagged ligands, which then bind to Notch receptors on neighboring smooth muscle cells. That leads to upregulation of, or activation of the Notch signaling pathway, upregulation of Notch receptors and jagged ligands, and then that feeds forward to the next layer of smooth muscle cells, etc. And the Notch pathway is very important for differentiation and homeostasis of smooth muscle cells. So if you have a mutation in the Notch pathway, this in many cases is lethal, and otherwise you often have different pathologies that are all related to mutations in the Notch pathway. So it's a very important pathway, and we're interested in how can we leverage the pathway to influence regeneration towards getting better outcomes. So I do this work together with Cecilia Salgren. She's a professor in Finland, but she's a cell biologist and an expert on Notch signaling. I'm not, so I'm happy to do this together with her. So very simplified, this is how it works. So we look at Notch signaling between smooth muscle cells, where we have jagged ligands on a signal sending cell that bind to a Notch receptor on the receiving cell. So whenever you have these binding of these ligands and receptors, that leads to cleavage of the intracellular domain of the Notch receptor, that translocates to the nucleus, and there it activates all kinds of pathways. And it leads to differentiation of the smooth muscle cells. So the interesting thing from a mechanobiology point of view is that the expression of these ligands and receptors is dependent on the mechanical environment of these cells. So if you have low strain levels, smooth muscle cells express a lot of ligands and receptors, so you have a lot of Notch signaling going on. But if you have higher strain levels, then that leads to a reduction in these expression of ligands and receptors. And you can imagine that that influences cell behavior. So in that way, Notch can explain, at least to some extent, why cells respond differently in different mechanical environments. So what we did in a first study, this was actually done by a master student at that time, Fleur Terhune. She actually looked into the role of Notch signaling, and particularly its mechanosensitivity, to establishing vascular homeostasis during development. So this is application to native blood vessels. So we wanted to understand, okay, how does this mechanosensitivity of the pathway influence the establishment of vascular homeostasis? So we did experiments in the lab. They were done by a postdoc, Oscar Stassen. He strained vascular smooth muscle cells with different strain levels and looked at how these receptor and ligand expressions changed with strain. And then these data were informing a relatively simple 1D computational model. We made use of symmetry of the blood vessel, so we could just use a 1D cross-section where we had an endothelial cell and then different layers of smooth muscle cells, and the number then is dependent on the wall thickness that we assumed. And then between all the cells, we had these protein interactions that were involved in the Notch pathway. And then we included the mechanical state via an analytical equation, the Laplace equation. So what we wanted to know is, okay, if these blood vessels develop, when do you actually reach homeostasis if they grow? How does that work? So we started off with relatively thin blood vessels, so with a low wall thickness, and then our model predicted that if you have a low wall thickness, then most of the smooth muscle cells are not differentiated. They're still kind of in a growth state, so there's no homeostasis yet. And then when you increase wall thickness, then at some point you actually cross a certain boundary where most of the cells actually differentiate. So it increases Notch signaling, and then you get differentiation of the smooth muscle cells. And this transition thickness where this change from non-differentiated to differentiated smooth muscle cells happened was actually pretty much in line with the actual thicknesses of blood vessels that were known from the literature. So we simulated different types of vessels, and the shaded areas here are the reported anatomical thicknesses in the literature, and the transition thickness where this change in differentiation status happened actually matched quite well with our model predictions. So at least this suggested that Notch indeed has a critical role in establishing and maintaining vascular homeostasis. But of course, this is a very simple model. Notch is not the only pathway that is important for vascular cells. So we also did some experiments to really dive into, okay, how important is Notch actually? So this was work done by one of my PhD students, Jansu Karakaya. So she cultured vascular smooth muscle cells of both extremes of the phenotype, so synthetic smooth muscle cells and contractile smooth muscle cells in the lab. So here's an alpha SMA staining showing that the contractile differentiated smooth muscle cells are indeed more contractile than the synthetic smooth muscle cells that are not differentiated. So what she then did was she inhibited and activated Notch signaling to see the influence of Notch on smooth muscle cell differentiation. And what she saw was that if you inhibit Notch signaling, then for the synthetic smooth muscle cells, which were already not differentiated and not contractile, there was of course not so much to lose. But for the contractile smooth muscle cells, they indeed lost part of their contractility if you inhibit Notch signaling. At the same time, if you activate Notch signaling, then that leads to an upregulation of the contractile features of smooth muscle cells. So this shows that at least you can directly influence the phenotypic markers of smooth muscle cells via the Notch pathway. And then the next question is, of course, what happens if you apply mechanical stimuli? What is then the role of Notch mechanosensitivity? Jansu strained these cells with different strain magnitudes in the lab. And what she saw that, so these are the static samples, these are the strain samples, that we saw a reduction of the contractile markers of these smooth muscle cells upon straining. So we saw that on the stainings, but also on qPCR data. So the orange markers are the contractile cells, the blue ones are the synthetic cells, that we saw really a decrease in contractile features with strain, which were correlated with a decrease in Notch signaling. So Notch signaling actually decreases indeed with strain, and it's correlated with a decrease in contractile properties. And of course, a correlation doesn't mean that it's also a causative effect. So Jansu also activated Notch signaling during straining, and there she saw that if you activate Notch during straining, you can partly rescue the loss of contractile features. So again, showing that Notch can directly influence the phenotype of smooth muscle cells, also under strain conditions. So then we wanted to analyze, okay, so because these were simplified in vitro experiments, what does that imply for vascular long-term remodeling? So for this, we collaborated with Jay Humphrey's lab at Yale University, where we tried to integrate this Notch mechanosensitivity into constrained mixture models. So a constrained mixture model, as the name said, it's a mixture model, so we have different tissue constituents that are enforced to deform together, and then they can individually turn over. So you can have growth of different constituents, but also, and also remodeling. So how it conceptually works is we have an artery, and the artery is a nice thing because you can analyze the mechanical state analytically. You don't need a finite element model for that. So based on the dimensions of the blood vessel and the loading conditions, you can analyze the stresses and also strains if you use some assumptions there. And then these mechanical states served as an input for our Notch signaling model. And since Notch is not the only pathway, we also had a black box phenomenological component in our model to compensate for all the other pathways that are important in vascular growth and remodeling. And then this Notch signaling activity and the phenomenological stimulus led to collagen production, smooth muscle cell proliferation, which then affects the mechanical state, and then you continue this feedback loop over time. So this modeling framework was developed by another PhD student of mine, Jordi van Asten. So a little bit details of how this works. So we have different tissue constituents. So for blood vessels, we have smooth muscle cells, collagen fibers, and elastin. And elastin was assumed not to turn over. It just stays constant after birth. But smooth muscle cells and collagen could actually turn over. So you have basic turnover rates, so you have production rates and degradation rates, and in homeostasis they're in equilibrium. But if you're not in homeostasis, then they're not in equilibrium. So you can have more or less mass production than you have degradation. And that difference in mass production from degradation is regulated by a stimulus function, which is dependent on, in the classical models, on the mechanical state, but we also made it dependent on our Notch signaling model. So we have basically three inputs: our Notch signaling model, the intramural stress levels of the vessel, and the wall shear stress, which is also a relevant input. And then very briefly, what we had is we had our notch signaling model. The equations don't matter, right? I'm just showing here to link them what is actually in there, but you don't have to know what's exactly about. So we have ordinary differential equations to model the protein interactions. And then the amount of notch activity in the cells served as an input for our notch stimulus function to regulate smooth muscle cell proliferation and collagen production, which we then based on our in vitro measurements of how notch expression relates to collagen production and also smooth muscle cell proliferation. And then we had phenomenological stimuli. So if you have a deviation in your intramural stress or your wall shear stress, that also leads to increases or decreases in mass production. So we first applied our model to analyze native vessel adaptation. So in this case, to hypertension, because there was experimental data to compare our model to. So if you have hypertension, then your blood pressure increases. That leads to an increase in the stretch in our blood vessels. And our model predicted that this would lead to a decrease in notch activity in the smooth muscle cells. And together with this black box component, the end result was that we get an increase in collagen and smooth muscle cells and an increase in wall thickness to lead to a new equilibrium. And what we learned from this model was that our notch signaling model was really important for getting the smooth muscle cell proliferation correct, but it couldn't capture the increase in collagen. So for that, we really needed the black box components. So in this way, yeah, we modeled the notch pathway mechanistically, but it also shows what it cannot model, because yeah, it does, of course, not explain everything. The benefit, however, of the mechanistic model is that you can look at manipulations of the pathway. And the relevance of looking into that is that for tissue engineering, we can actually integrate scaffold materials with, for example, these jagged ligands. So we can connect them to the scaffold materials, and these ligands can then activate notch signaling in the cells that invade these scaffolds. So in that way, you can influence notch signaling in these cells. So with our model, we just investigated what happens if you would activate notch signaling in at least this case of hypertension as an example case. Yeah, so if you activate notch, then obviously you get an increase in notch activity. And the interesting thing was that our model predicted, so we don't know if this is true, we should still validate this, is that you get indeed an increase in collagen production and a reduction in smooth muscle cells, but the long-term results are actually quite limited. It's particularly a short-term effect. If you do that, long-term, there's not so much dramatic changes. So the question is how important, yeah, what is actually the, how promising is this strategy actually? We don't know yet. In the next step, this is Jordi's final work of his thesis. We used the model to then look at the regeneration of tissue-engineered blood vessels. So we first looked at a native case because that was more simple, but now we also wanted to model the complete transformation from a synthetic blood vessel to a living tissue. So we have a scaffold material which invokes an inflammatory response. I have to say this inflammatory response is pretty much prescribed, so that should be improved in the future. But that inflammatory response leads then to infiltration of smooth muscle cells that leads to also collagen production. And under the influence of mechanical stimuli, and also the stress shielding effect of the scaffold material in the beginning. So the cells in the beginning don't feel so much of the mechanical loading. And then again, that leads to notch signaling and a phenomenological stimulus to influence growth and remodeling, to in the end up with a living blood vessel. So with this framework, we analyzed, okay, what is the influence of varying patient-specific conditions, and also can you reduce the variability between different patients by activating or inhibiting notch signaling? So long story short, this didn't appear to work, so I won't show you anything there. So it does have an influence, but it doesn't decrease the variability. But in terms of differences between patients, I'd like to show you two examples. So in one thing, so we had a reference case of tissue-engineered vascular graft regeneration that we based on known data from in vivo experiments. This is the dashed line. So we varied the inflammatory response, because if you have a certain disease, that you can have more or less inflammation to a foreign material. This showed that this only has transient effects on the regeneration of these blood vessels. So we have short-term effects on collagen and smooth muscle cells, but the long-term effects are pretty small, and particularly at the functional level, so the luminal radius and the compliance of these blood vessels, there was hardly any effect, which may be due to the fact that this inflammatory response was prescribed and only short-term, but at least this is what our model predicted. On the other hand, if we would vary the degradation rate of these scaffolds, which also can be correlated, by the way, by having a different inflammatory status. So having faster degradation or delayed degradation of these scaffolds, this showed that this can actually trigger more long-term consequences. So the differences may start small, but at some point you can enter positive feedback loops and you can really push the regeneration out towards a different equilibrium or not even an equilibrium. So this shows that these differences in degradation rate can actually have long-term effects, and this is probably a factor that we need to seriously consider because it also affects the functionality of these vascular grafts. Yeah, so that's about this notch signaling work. Then the final work where we developed some computational models to really integrate growth and remodeling. To model this entire transformation from scaffolds to living tissues, and then particularly apply to heart valves. Because for the blood vessels, we can use the constraint mixture model that I showed on the previous slides, but for heart valves, this is not possible. I'll explain you why. So our previous heart valve models of heart valve remodeling, they only focused on the adaptation of living tissues. We didn't have any growth in there. So if you want to include growth, you need to include this constraint mixture model approach that I showed you in our blood vessel work. But the problem is that these constraint mixture models are computationally quite heavy, so you cannot integrate those models with a finite element model. It's just way too complex. It's way too computationally expensive, and we need the finite element models to analyze the mechanical state of our heart valves. So in recent years, homogenized constraint mixture models came up. So we wanted to develop a homogenized constraint mixture model now to model the adaptation, so the growth and remodeling of heart valves. We didn't immediately start with tissue-engineered heart valves because there's not so much long-term data available for tissue-engineered heart valves. And the quality of the model is, of course, dependent on how much data there is to build the model on. And it's also biologically quite complex because you have the inflammatory response, the tissue-producing cells. So we thought, let's start a little bit more simple by looking at an example of native heart valve remodeling and growth. And this is the Ross procedure. So the Ross procedure is a procedure where you replace a diseased aortic valve with the pulmonary valve of the same individual. So you move the pulmonary valve, which was normally exposed to low blood pressures, to the aortic position where it is exposed to much higher blood pressures. And of course, in the pulmonary valve, you also need a valve. So there, typically an artificial valve is implanted. But because of the lower hemodynamic loading there, you can better have the artificial valve in the pulmonary position than in the aortic position. So in the aortic position, there is a living valve, but it will adapt to the higher hemodynamic loads. And this adaptation, there's some data out there. It typically shows that the thickness of the leaflets increases quite substantially after the Ross procedure. And also the tissue composition changes from this kind of configuration towards this configuration where you see much more fibroelastic tissue formation. So the constraint mixture models, to explain the difference with the homogenized framework, are not, you cannot implement them in a finite element setting. So the homogenized frameworks are basically a combination of constraint mixture models and more simple kinematic growth models. So kinematic growth models, that's mathematically a quite simple approach where you just prescribe the growth of a material without any remodeling. So you can also not consider different constituents. And these concepts have been integrated into a homogenized framework where the kinematics is actually quite similar to the kinematic growth models. But you actually prescribe the growth for different constituents in your tissue. So you can still consider the different tissue constituents, similar to the classical constraint mixture approach, but we can actually include the growth in a more simple way, similar to the kinematic approaches. So we balance then the mechanobiological complexity with the computational expenses. So for the heart valves, we have 3 tissue constituents: collagen, glycosaminoglycans, and elastin. Elastin, again, could not turn over, so we only had 2 tissue constituents that could grow and remodel. Again, based on some stimulus functions that could be dependent on stress or strain. And then, again, the details of these equations are not relevant, but depending on a certain increase in the mass of a constituent and the difference from a certain homeostatic target and the stiffness of the tissue in different directions, we could actually calculate how the tissue would then grow in different directions. And what it basically means is that it tends to grow in the direction where the stiffness is lowest, so that it has least resistance to grow in that direction. So we first built a pulmonary valve that was homeostatic in pulmonary conditions. So we calibrated our model to lead to homeostasis in pulmonary conditions. And then we imposed higher blood pressure conditions similar to the aortic valve. So we either did that instantaneously and then simulated growth and remodeling for quite a long time. But we also applied the increase in pressure more gradually, because also there's different surgical techniques where also there's some debate about whether you should actually do this blood pressure increase more gradually via some drug supplying. From a more mechanistic point of view, we were also interested in understanding, is stress or strain the main driver of this adaptation? So we included both hypotheses in our model to see what works best. And I'll first show you the results of our instantaneous increase in blood pressure, assuming that the tissue constituents grow and remodel in response to differences in stress. So what this showed was that the valves, they grow substantially. This is then the mass density increase over time, particularly in the center of these leaflets. And this growth then translates into an almost doubling of leaflet thickness and a little bit smaller increase in the leaflet length in this direction. So they get a little bit longer, the leaflets, but primarily a lot thicker. And this is then what a cross-section of the heart valve, so at the center edge, looks like. So it starts to elongate a bit more, and it gets a lot thicker over time. Then if you look at the tissue composition, because we had turnover of the collagen and the GAGs, the glycosaminoglycans, well, the assumption of stress homeostasis led to a tremendous increase in collagen, which is also very much in line with the histological images that are reported in the literature. And interestingly enough, this is the collagen organization of the pulmonary heart valve, this dashed line. Our model predicted that after imposing aortic pressure conditions, the organization would actually become less anisotropic. This is really contradictory to what people believe, that where typically they believe if you just implant a tissue in a new position, in the aortic position, it will just adapt to an aortic valve. And an aortic valve has a much stronger alignment of collagen compared to the pulmonary valve. But our model predicted the opposite. And also by talking to a few people in other groups, they have also seen that if you impose pathophysiological mechanical conditions to heart valves, that you often have a decrease in anisotropy. So it shows that it doesn't automatically go back to, or it doesn't go towards the preferred physiological organization. Then here are the results for assuming stretch homeostasis or strain homeostasis. So we get different results. So we get more growth compared to stress homeostasis, a lower thickness, and a longer leaflet length. So the morphology of the valves is also different. So it really matters what kind of assumption you have for growth and remodeling. And looking at the histological data, we think now that the stress homeostasis is more appropriate, but this really shows that it matters what you assume, and that you should compare your results to experimental data. Also, in terms of tissue composition, we got really different outcomes. So we get a much more GAG-dominated tissue composition when you assume strain homeostasis compared to stress homeostasis. But surprisingly, the collagen organization was actually quite similar. And then finally, we compared this instantaneous increase in blood pressure to the more gradual increase in blood pressure. And there it showed that the gradual increase, of course, the growth is slower, but in the end, you end up with more growth, which then particularly is visible through an additional increase in leaflet length, because leaflet thickness was more or less the same. And this additional tissue length is actually quite beneficial, because one of the risks of the Ross procedure is that the root, so the connection of the valve, it tends to dilate over time. It's often a complication of the Ross procedure. And you can imagine that if that happens, it's better to have a little bit longer leaflets, because you have a little bit more protection for having a leakage of your heart valve. Yeah, and the tissue composition was actually quite the same. So the main difference is this the difference in leaflet length that you can get. So what we're currently doing, so we're also looking at repair strategies of heart valves. This is actually work done by a master student in our group. So we also, because this is a collaboration with surgeons in the Netherlands and in Denmark. So we also want to understand, okay, at least they want to understand how should I repair a valve in the best way possible, because they get really different types of heart valves when they do a surgery, and the repair strategy is probably dependent on the type of geometry that the patient has. So we have two questions basically here. So if you have because this is a repair strategy in response to root dilation, so the root dilates and the valve becomes non-functional, then how should you repair that? So they typically impose a graft surrounding this root to bring it back to its more physiological state, but the valve also adapts, so it's not really known how they should then treat the valve itself to also get physiological function. So with the master students, we have now looked into more short-term effects, so how should you repair a valve, and what is the immediate post-operative valve function if you repair a valve? And what we would like to know afterwards, how does this valve then adapt in response to this repair strategy? So that's something we should still look into in the future. So a student, Jur van Kimmenaar, is a master student. These are the two surgeons. So we really wanted to model the dilation of the valve, which leads to an incompetent valve at some point. And then the question is, how should we repair that? I'll just do that very briefly in the interest of time, but we modeled the root dilation in different ways. You can have a dilation mainly at the bottom of the valve or at the top, which also leads to permanent deformation of the leaflets, which we then included. This was an animation, but it doesn't work, but it doesn't matter so much. And then we modeled different repair strategies. So what if you bring back the root size to its original diameter or different diameter? What if you actually pull up the commissures? So these are these points here of the leaflets. And what if you also manipulate the attachment edge of the leaflets? How does that affect valve functionality? So here, the student has done different simulations with different graft sizes, and it basically shows that it really matters what graft size you choose, but also what you do with the attachment edge, basically, of the leaflets. That also influences the effective height, which is basically a clinical measure for valve functionality. I think I'll skip this part in the interest of time to have more time for questions, I think, right? Yeah, so we also now then, next step very briefly is that we also are working on implementing this growth and remodeling framework to analyze tissue engineered heart valves. What I showed you at the beginning was you implant directly this synthetic scaffold in the body to get regeneration inside the body. A more simple approach biologically is to first build this heart valve in the lab and then implant it. So you have this entire transformation phase in the lab without inflammation, which is more simple, and then you implant it. So what we're now doing, we're applying this framework to first look at this approach to see how we can steer that to get better outcomes. We do that together with partners in Zurich, because they have experimental data for us, where we can really quantify the properties of the scaffold materials, how that degrades, what are the mechanical properties, and then we can calibrate our growth and remodeling framework to get the measurements or the increases in thickness of the tissues that they also see in the lab. And then we try to model, okay, what if we now manipulate these in vitro conditions for creating a heart valve? What is the impact of that on in vivo adaptation, knowing that valve geometry has a very important impact on the ultimate remodeling and functionality. So this is to be continued. We're still working on this. So in summary, I showed you what we're working on in terms of remodeling, which is a bit older work, biological mechanisms and growth and remodeling. So at least, here we could really show that you can really change the outcomes of remodeling by changing the mechanical state and get better outcomes in terms of tissue engineering. We developed a hybrid modeling framework where we can analyze the mechanisms of certain biological pathways to understand how you can influence regeneration and adaptation. And we also now have a framework that can capture growth and remodeling simultaneously to understand more about how this happens in native tissues, but also in engineered tissues. And with that, some future directions. I think it's really important to integrate experiments and modeling. it's always a bit dangerous to just have modeling assumptions which are not compared to any experimental data. And I think now in the recent years and the upcoming years, there will be so many data, quantitative data, that is really good for computational modeling also to build better models. And with these models, I hope that we can advance also regenerative medicine. I do believe that we should also focus on the biology. It's really complex, but I think we really need to do that in order to understand what's going on. And to really do that, I think because this is very complex, I really believe in the concept of hybrid modeling, where you basically integrate physics-informed modeling with artificial intelligence methods to make a next step here. And with that, I would like to thank the people, particularly the PhD students and master students that did the work. I'd like to thank you for your attention.
Sandra, thank you very much for this impressive talk and research. So this is open for discussion. So maybe what we will do is that first we will check whether we have questions online. So I can stop sharing. Do you think you will need the slides, or?
Depends on the questions, but I think it's okay.
Okay, I stopped sharing for the moment to have online people. Okay, so online, do we have questions? Okay, so you're on the computer sound, so I'm not too sure I have heard properly, but your question is whether, so how they have dealt then with the different timescales between biological processes and the mechanical events, right? That's okay.
Yeah, that's a very good question. Very valid question also. So I basically have two answers. So for the third part, where we have the growth and the remodeling, what is a typical assumption in the constrained mixture models is that the growth and remodeling is only dependent on the maximum loading of the tissue. So for blood vessels, this is the systolic loading. For heart cells, it's the diastolic loading. So we actually ignore the transient differences within each heartbeat. Whether that is correct or not, well, it's probably not correct, but the assumption is that that is the stimulus that the cells are most responding to. And that is the driving factor of the growth and remodeling, which is more long-term. So in our the consequence of that assumption is that we don't have to include these transient effects over the heartbeat. We can just can take larger time steps, and then you can simulate such long periods. So that's one answer. For the first part, where we really model the influence of cells on remodeling, there is very well known that cells are responsive to strain rates, so really the dynamics that occur within the heartbeat. So there we couldn't really ignore that, we knew that. So there we used a mathematical approximation that was done by Tommaso Ristori, who is a colleague of mine, he's a mathematician, and he came up with an analytical approximation of our actin stress fiber remodeling framework, which is actually predicting the cellular organization and contractile forces, which allowed us to incorporate the dynamic changes within a heartbeat in a more phenomenological way. So again, to not have to simulate every single heartbeat over a period of 2 years or so. So there was a mathematical approximation for that, and we of course tested that this error was not too much. Yeah. I hope that clarifies your question.
Yes, thank you.
So, further questions in the audience? Yeah, Andrew.
Hi, thank you for the talk. It's really impressive, the amount of work that you've done. I've seen that now you're going to try to remove the inflammatory component through the in vitro modeling. But I was wondering on the not signaling simulations, how did you incorporate the inflammation in the process? It's like just a curve for a parameter, or do you? Yeah,
that's also a very good question. So the inflammatory response, we just incorporated in the way that is always being done in the constrained mixture model approach. So what is currently done in the constrained mixture models that are applied to tissue engineering is that the scaffold degradation is prescribed over time. And the inflammatory response, so you have a mechanomediated growth and remodeling response, but also in inflammatory mediated response, it linearly scales with the amount of scaffold material that is being present. So you basically also prescribe the inflammatory response. And you can scale that, of course, so that's what we did to see does it matter. But yeah, one of our future goals is also to do that a lot more mechanistically, to really, because for heart valves we know it's not homogeneous, so you cannot just prescribe it, and we try to also understand why it is not homogeneous. So we try to look more in the mechanisms of, okay, how do macrophages actually degrade the scaffold to build a more mechanistic model and just prescribing over time. Yeah, so that's definitely an important next step.
Thank you.
Yeah.
So just, I give you the word just to follow up a bit on this, because I had same question. So you're basically then assuming the activation of the toll-like receptors, no? When you do that?
It's really phenomenological. It's just what it actually does is, so you have scaffold which is being present, right? This is the constituent material, which has mechanical properties. Depending on how much scaffold there is, you basically influence the growth and remodeling of the cells and the collagen. So it's really, there's no mechanism whatsoever. It's just the more scaffold there is, the higher this inflammatory stimulus is.
So I suspect that the underlying mechanism, biological mechanism, is actually then the activation of the toll-like receptors of the macrophages and as byproducts.
Yeah.
So
the
experiments was
that we're planning to do that.
And byproducts. So we could give you a mechanistic clue on whether this is a reasonable assumption or whether.
Yeah, what we're trying to do. So I recently hired a postdoc exactly to work on this.
Okay.
So to do experiments where we really try to understand, okay, so macrophages produce cytokines. These cytokines influence the fibroblasts, which can then lead to different matrix production levels or different activation levels of the fibroblasts. So we want to understand the crosstalk of the macrophages and the fibroblasts in a systematic way. Yeah.
Thank you. Great talk. Great job. Can you develop a little bit more on the exactly what parameters you influence and what do you mean by prescribing? Is it putting some threshold or? And then the second part of the question is, can you generalize this inflammatory process to other types or all kinds of tissues?
So to start with the second part, so since we have this homogenized framework now, you can actually impose that to other types of tissues. So the classical constrained mixture framework, because you'll use the analytical equations for the mechanical state, so you're just limited to simple cases, right? So the blood vessel has the benefit that it's symmetric, and there's an analytical equation for the stress state and the wall shear stress. But for any random type of tissue, you cannot use that. And that's why we developed the homogenized framework to allow for much broader implementation. The first question was about the development of how we actually did the inflammatory response.
Yeah, more details about which parameters affect which ones.
For which model? Or
for the inflammatory response.
Yes. So we have a scaffold material which is responsible for the inflammatory response. And that is just a constituent material. It has a stiffness, and the volume fraction and also the stiffness, they vary over time. That is prescribed now, based on experimental data, but it is prescribed. Whereas normally it should be cell dependent. So that's what we would like to do next. But the volume fraction of the scaffold then also influences how much collagen production there is by the cells that are in the tissues. So it's really phenomenological.
Yeah. So, and again, the degree of inflammation, so you have a kind of one variable.
And you can scale that. It's kind of a gamma function, and we scale the amplitude of that at this stage.
So it influences basically the volume fraction of the scaffold.
Yeah, the volume fraction of the scaffold determines everything, basically. And then the amplitude of how that is scaled with the inflammatory response.
I think I would read your papers better. Thank
Well,
you.
that last thing should still come out. So, but I would advise you to read the papers of Jay Humphrey's group because they pioneered this whole framework, this inflammatory mediated growth and remodeling for vascular grafts. And I think they really pioneered this. They made some very important first steps in this direction. So you can find all the details there. And we just used their framework and we collaborated with them to apply it to our cases. Yeah. So all the details are also in their papers. Yeah.
Thanks.
Yeah.
Hi. One question. If you have a problem in the bulb tissue, like calcification or stenosis or something like this, and then you regenerate it with this, well, with what you explained, this new bulb wouldn't have the problems that you had before, or wouldn't be affected?
That's a good question, because also something we should look into in the future, because we assume, at least most cases, you assume that regeneration goes according to healthy processes, right? But typically you replace a tissue in a diseased patient, where regeneration is different. And they probably have all kinds of other comorbidities that influence the regenerative capacity. And it also depends on age, etc. So there's many things that influence this. And particularly also, so for example, a blood vessel, you typically take out the disease part. That is the idea, and then you really, you implant this scaffold as an interposition graft. So you don't, there is no stenosis or calcification then directly connected to the graft, if you do it like that. But there's also approaches where you implant the scaffold inside a diseased artery. And of course, there maybe you do have some effects. But we know very little still about that. Yeah, it's a very important question to take into account. Yeah.
Okay, thank you.
I might have a question. Well, on your slide 31, it was about smooth muscle cells. It was about the stimulation, activation, and inhibition that I think a PhD student did for the smooth muscle cells to see what they react for this notch pathway. How did you actually activate and inhibit? Yeah. Like how was this specifically done?
Yeah. So for you refer to the experimental data, right? So the inhibition was done via adding a chemical that inhibits the cleavage of the notch receptor. The activation was done by coating the surface of that the cells are binding to with jagged ligands. So they bind to the ligands, and then that activates notch signaling directly.
Okay, and then a follow-up question on that. Could you somehow consider physiological values for this activation and inhibition? Because this is something I see often in this research field, that we overstimulate cells with So, like, how physiological was then this activation and inhibition? Could you control that?
That is a very good question. I honestly don't. I don't really know. Honestly, we just looked at it doesn't matter, but is that physiological? I think that's difficult to answer also because we also don't really know, particularly not in regenerative settings, what is the connectivity of the cells, right? Because notch is a juxtacrine pathway, so you need to have direct cell contact to have notch signaling. So do we have a physiological cell density? Probably not. And that also matters for notch signaling. So the question is, in native tissues, there's probably this more dense. So and then is that physiological? Well, it depends on the situation, how much notch signaling there is also, because we also see it's dependent on the mechanical state, maybe probably a lot of other factors. So I also don't know if there's only one physiological answer to compare to. So yeah, I think it's a very valid question. I think the most likely answer is no, we're not mimicking the physiological situation. What that is, I think, is also very difficult to know, and it depends on the situation that you are in. And the notch pathway is also pretty notorious in the sense that it's really context dependent. So if you're in a different artery, you have different ligand and receptor expressions, which also influence the notch pathway activation. So it also complicates things.
Thank you. It was a really impressive talk.
Thanks.
Thank you as well. I have a question for the mechanical design of the valve. I think you have to, at one point, have the mechanical, stability of the scaffold, but also allow for, enough, stimuli for the cells. How do you, maybe you can, talk a bit about, how you, what's the main consideration, and how to keep it when the degradation happens, to always have enough stimuli?
Yeah, that's a very good question. I don't have the entire answer, but what most people in the field think is that we should design our scaffolds to replicate the physiological valve, or physiological blood vessel. And I actually question that, because if you do that, then the cells are not activated. In the beginning, you want to activate them because they should produce new matrix and they should proliferate, etc. So I don't think we need to resemble the physiological state at the beginning. We should design something that triggers the evolution towards the physiological state. But what that initial state is, I think that is still very unclear. And what we do see for blood vessels is that it's for some reason it goes better automatically. So also because it's more of a constrained tissue, I think. So, and you only have to get the radius and the thickness right. So it's more simple geometry. The valve is really a complex 3D structure. It's also difficult to measure the actual physiological geometry because there's always pre-stretches involved and everything. So if you cut it out, it shrinks. And yeah, and you can never measure the geometry in vivo because it's always loaded. So it's also difficult to analyze actually what is the actual in vivo physiological state. But I think, yeah, we really don't know yet what kind of environment we should provide to, in the end, get a physiological organization. That is actually a very important key question. And I think it's too easy to think, oh, if you just provide a physiological scaffold environment, then it will go right. I'm not sure, actually. Yeah.
So, actually, well, I have tons of questions, but I will limit myself to a couple. So I have one technical question. So you probably have, so you're using then the homogenized growth with deformation gradient tensors. So, but you're most likely have non-affine strengths, which will have huge effects. So have you been able to look into that to somehow quantify this possible non-affine strain that would make then your predicted biological cue or assumed biological cue not be aligned with homogenized mechanical fields?
In a very simplified way, so we have the different constituents and they all are deposited at their own assumed to be physiological pre-stretches. So the collagen can have a different strain than the gags, for example. So at the constituent level, the stresses and the strains are different. And that's also why if you assume stress or strain homeostasis, you get completely different outcomes. Of course, the actual situation is much more complex. If you have a fibrous organization and you would strain that, then the overall deformation gradient tensor is not what all the cells feel. They feel something different. That we haven't done, but in a homogenized fashion, we have at least accounted for differences in actual strains experienced by different constituents. But I think for what you ask, and it's a valid point, I think you need more microstructural models to zoom in. Yeah. But we also don't know what they actually then experience. And also if you measure something in the experiment, it's also you measure bulk, so outcomes. So that's also difficult to quantify.
I guess you can measure very, very local deformations through so pixel correlation analysis. So if you're able then to deform your material under a microscope. So
yeah, maybe you can, but then also the question: can you also quantify growth and remodeling at a local level, or do you still measure bulk?
Yeah.
But yeah, it's an important point. Also, so even if they would feel the same, what are they actually feeling? We don't know. Yeah. That's definitely a limitation, and so yeah, it works, but it doesn't mean that all the underlying assumptions are all completely correct. Yeah.
And then the other curiosity I had is that so you've basically then to modify the shape, so in order then to avoid this compression that would favor cell contraction and valve retraction. So when you have these more planar shapes, so basically then you have so shape discontinuities with sharp angles.
Yeah.
So as far as I understand, nature would not like that too much and would tend to smooth everything out.
Yeah.
So is that something that you're observing and then contributes with long-term greater retraction of the valve, or?
Yeah, so we are definitely looked into that. So we also see in the models you get stress concentrations at exactly these hinge points, basically. So it's probably also the point where they will fail at some in time. We haven't seen that in the in vivo studies, maybe because they also do remodel into something more smooth. But another PhD student that I co-supervised at the University of Zurich, she actually came up with a different design that shares kind of similar features, but it's more smooth. So she published a paper also recently, a few months ago, where she compared those two designs. And she also showed that actually more smooth design leads to lower stress concentrations and probably is better to use. Yeah.
All right.
Yeah.
All right. Okay, great. Any further question? So maybe just to finish with, so since this is a summer school, I would have a question about career development. So your experience. So you've done your PhD and you have traveled a lot. So before going back to Eindhoven and then finally stabilize. So if you could comment a little bit on this experience and how instrumental it has been then for you.
Yeah, that's a nice question.
To a point of competitive research. So you had an ERC, you had a VD grant.
Yeah.
And and
that's a very nice question.
No? So
yeah, maybe also to comfort people, I think I did a lot of things wrong. So, because I think what people typically say is if you do a PhD somewhere, or you should go somewhere else for a postdoc, right? That's good for your career. Well, I didn't want to do that because I did travel in my PhD for just a few months, also as a postdoc, but it was all temporary. I was always based in Eindhoven. And I didn't want to go abroad just by myself for 2 years for a postdoc. Because it was, I knew chances of getting a career in academia are very limited. Why would I be the person to get a career in academia? I think I didn't really see that happening. So I think, I don't want to risk everything to go abroad for 2 years, leaving my partner behind, without having any guarantees that this will actually lead to something successful. And then actually my PhD supervisor had a very nice postdoc project for me. And he just said like, don't worry, if you get grants, you will be fine. Of course, I didn't get the grants, so at the end of the postdoc, I thought, okay, this is the end of my academic career. And then I got offered an assistant professorship position, still in Eindhoven again. So I stayed for everything in Eindhoven. And then I still wanted to go somewhere else, but not for career reasons, but because I just wanted to go to Stanford. I wanted to learn more about modeling growth. So I applied then for the Marie Curie Fellowship, and at some point I was lucky. I also had very nice colleagues that helped me with writing grant proposals. I think this is also a learning experience, right? I failed a couple of times in the first years. But you shouldn't give up, apparently, because it can also, after a few years, you can be lucky. So, but I only did it because I wanted to do it. And not because it was good for my CV or career or whatever. I really don't believe, of course, you shouldn't do too many stupid things, but I think you should also do something that you really like to do. And not be only guided by what is good for your CV. And also, what I really like in my research is to collaborate with people with different expertise. I think you really learn a lot from this cross-disciplinary collaborations. So the collaboration on notch signaling with this professor in Finland. Yes, he was then a part-time professor in Eindhoven. When we started this kind of explorative project with a master student, it was really because of some curiosity from both our sides. Hey, can we combine things and then do something new? That was the basis for my starting grant. So because we're just doing something new, it wasn't extremely difficult, but it was just new. And that's why, that was, I think, the key of getting the grant also. It was different from what other people did. So I think main advice is just follow your interests. And I think that's the only way it works, right? So,
Right, great. So I think it's a nice message then to shift to the coffee break. So thanks again, Sandra.
Yeah, of course.